Okay, so in this second part of the video on the power function, what I would like to do is just explore these various points in my source code 1, 2, 3, and 4, and just give you some intuition that it actually, I mean, what we just did here algebraically, it actually holds my loop element actually holds at these various points over here. Now, one other thing, if you're just curious, think about this. If if this code in yellow, let's just think about this for a second here. If this piece in yellow isn't visible to you, just think for a second that it's completely invisible. I mean, let's just cross this out just for time being. Okay, if I'm going to cross this out, okay, and if my loop invariant is really strong to begin with, if the loop invariant is very strong to begin with, can I actually confer without even stepping to the code, even before even going each iteration in the code, can I actually infer what is result going to be just by reasoning through my loop invariant? Okay, so what does that mean here? What is the value of result going to be? What is the value of result going to be just when this method returns this value result here? And so let's think it. So that means at point four here, at point four here, what is my x going to be? Well, my x doesn't change. My x is still going to be the same as it is. My a hasn't changed. A is still going to be as it is. Okay, so I have x to the power of a equals to what is y? Y isn't changing. Y is still going to be as it is what it was previously. What is b going to be? Okay, I just said earlier in my last video that b is going to be equal to 0 because when b is 0, the loop breaks, the loop terminates. When the loop terminates at b equals to 0, what I have now is y raised to the power of 0, where b is 0, times the result. So my question earlier was, what is this result going to be? So if y to the power of 0, anything which the power of 0 is 1, meaning result must be x to the power of a. So because my loop invariant was so strong to begin with, I could easily, even without stepping through these various points in my source code, right, without going through every single iteration of this thing and build up my result, I can just straight away reason through the loop invariant, looking at this point for what is my x, a, y, b going to be, and using that knowledge, I could easily confer that result is something that must actually be x to the power of a. Okay, so again, what I'm trying to get at in this video is that there are two different ideas that you could be looking at in getting your power function implemented. One, in this, what I've done here is I'm decrementing b by 1. I'm doing this in a very linear fashion, but you could also decrement b by half. And if you were to take that approach, then you do get many simplifications, and you would need to consider about b being an odd or an even, and I highly recommend you to explore that idea using loop invariant and getting your power function implemented where b gets reduced by half. What I've done here is b gets reduced by 1. Okay, so again, if you want to, if you still aren't convinced by this what I've done here at point 4, you could also do something where I could create these various points 1, 2, 3, and finally my point 4, and I could, for each of these points in my source code, I could play with some values where I can say, all right, what is x going to be at this point, what is y going to be at this point, what is result going to be at this point, and likewise what is a and b at these points here. And just as you go through this loop here, you're going to see that for whatever b and result that changes, my loop invariant is still always going to be x to the power of a. So let me just do at least few of these things. In fact, let's do this. Let's play with some small numbers so that I can actually show it to you. This actually works out. So let's just do this. Let's say the function gets called with x equals to, let's just make x equals to 3, and let's have a equals to 2. So at point 1, I have x equals to 3. I have y equals to 3 as well, and I've got my a equals to 2. I've got my b equals to 2. So what should result be? Well, if this is my loop invariant, I already know what xa is. I already know what yb is. The result is something that must be equal to 1. So my result matches right there. My result is 1. Okay, so right at this point 1, just before the loop begins, my result must be 1. At point 2, because nothing has changed here, okay, this condition over here has no side effect. Because it has no side effect, nothing has changed here. And at point b, at this point 2, let's just get rid of this b here. Okay, so at point 2, I still have my x as 3. So I still have my x, y, and the result, and a and b, all just being carried forward from 1. So these values are still 3, 3, 1, 2, and 2. Okay, what happens at point 3 now? Well, at point 3, result has changed. We have result equals to result times y. So if result is 1, 3 times 1 makes result as 3. So what I have now is at point 3 here. So let's just make this a little clear. So this is my point 1. This is my point 2. And I can see that result at this point is equal to result times y. Y is 3, result earlier was 1, 3 times 1 is 3, so I've got my result as actually equal to 3. My x and y haven't changed, meaning my x and y are still going to be the values that I had previously, which is 3 and 3. And likewise my a and b at this point 3, a is still going to be 2, but my b has decremented by 1 because I have this b minus minus. And because b has decremented by 1, if b earlier was 2, b now is going to be 1. Okay, does my loop invariant hold here? What is x to the power of a? 3 to the power of 2 is 9, equals to y raised to the power of b. Y in this case is 3, and 3 raised to the power of 1 is 3, times 3, meaning it's actually 9. So let's just do that just to check the loop invariant at this point here. I have my x as 3 and a as 2. I've got my y as 3, and I've got my b as 1 times result. The result is 3, so I can see that 3 times 3 is 9, and my uh, x to the power of a is also holding, meaning this is also 9, so my loop invariant holds here. So just step through this code, one more iteration here, couple of more iterations here, and you'll see that it holds at every single time. At every single iteration, the loop invariant holds every single time. And because the loop invariant holds at every single time, by the time the loop breaks, my result is something that's just going to be equals to x to the power